All right, so let's start chapter 4 with the same method, same steps. Step 1. Step 1, we have 4 drawers. Force on a current carrying conductor. Sounds a bit too wordy. Maybe we can focus on current carrying conductor. Right, the conductor is not the bus conductor. The conductor is the conductor that is able to conduct electricity, like copper that is in your wire. Right, so the opposite of conductor is insulator. Insulator is the material that is not able to send or transport the electricity. So current carrying conductor, the current is the current, the electricity current, which we learned in chapter 3. Right, so there is a current, there is a conductor that can carry current. Right, then number 2 is the electric motor. Number 3 is the electromagnetic induction. Number 4 is transformer. Right, so you have electricity, you have electric motor, you have electromagnetic induction, and you have transformer. Now, how do you remember the 4 drawers name? Imagine the story of you force current train conductor to ride on electric motorcycle that stick a magnet and became a transformer. Right, so this current train conductor is the train conductor. If you took train before, there are people who ask you for the ticket. That is what we call train conductor. So you force this Mr. Train conductor to ride electric motorcycle, and then when the electric motorcycle stick a magnet into it, and it become transformer. Right, so it's a very silly story. It doesn't make sense, but the objective here is to help you to remember the name of the drawer, as you know. Right, so you can imagine current train. Let me play this very short video. If you cannot see it properly and hear it, let me know. Okay, it's only a few seconds.
Form 5, Chapter 4. Electromagnetism. You force current train. Conductor, ride, electric motorcycle. That stick, a magnet, and B, transformer.
Okay, so let me just break down a bit.
Form 5, Chapter 4. Electromagnetism. You force.
Right, you see, this is the train conductor. They dress something like this. So you force your current, which is the noun, train conductor, to ride electric motorcycle. So rather than being on the train, doing his job, checking the tickets, you force him to ride electric motorcycle. And he's so happy.
Current train. Conductor.
Okay, then when you stick the magnet on it, on the motorcycle, what happened? It became transformer.
Ride, electric motorcycle. That stick, a magnet, and B, transformer.
Right, it became a transformer, right? So that is the story for you to be able to remember the 4 drawers name, right? So now you have current carrying conductor, then you have electric motor, which is, okay, current carrying conductor is you force current train conductor, so the force on a current carrying conductor to ride motorcycle, electric motorcycle. So second drawer is electric motor. Then you stick a magnet. That magnet is trying to help you to remember electromagnetic induction. And then, of course, the last drawer is transformer. And that electric motor that suddenly became a transformer. So that is the story, right? Now, drawer, step number 2. Let's move to step number 2. I need you, okay, again, how do you read this step number 2? Number 1 is you are building your knowledge for this step, for this chapter 4. And now, from the scale of 1 to 10, 1 is the lowest, 10 is the highest, you are probably at level 1 or level 2, right? So let's read this with the intention to build it to level 2. Level 2 means that out of 10 questions, if you get 2 correct, then this is fine. This is what you should be expecting at this level. Right? We will be building it to the level 9 as we always do after 2 hours, right? When we follow step 1 until step 9. Now, let's take let's say 2 minutes to read drawer 1 and drawer 2. Let me just pull out the clock. Okay, you can start now while I'm working on the clock. Okay, drawer 1 and drawer 2. Okay, time's up. Let's do drawer 3 and drawer 4 for 2 minutes. Okay, good morning, Aiden. Okay, while Singling is reading the step 2, Aiden, we are on step 2, and there are 4 drawers.
Okay.
Okay, and now we are reading drawer 3 to drawer 4 for step 2. I'll give you a quick recap, but for now, let's do this. You read drawer 3 until drawer 4 for the remaining of time. Okay, So let me do a quick recap. Aiden, I sent this link for the AI animation video, the very short video where it contains the main story and also the story of each drawer, right? And you can play it quickly to see if you are able to play it on your computer. Usually if I play on my computer, you told me that you experience lagging. All right, I'll give you a few seconds just to play it. Okay, the first few seconds is fine. If you're the first few seconds is important for now. If you're able to play it in your computer, on your computer, then let me know. Okay, then if you're able to play on your computer, let me know. Aiden, are you here? Okay, can you hear us? Yes, you can play. I see it.
Yes, I
Right,
can
good.
play. Thank you, Uncle Alan.
All right. So the purpose of that very short video is to help you to remember the name of the drawers, the first few seconds, right? The first few seconds, if you realize, the first few seconds is illustrating this very short and silly story. So what does it mean? You force your current train conductor. Train conductor is somebody who check your tickets when you are traveling on the train, right? You force him to ride on an electric motorcycle. And then that electric motorcycle stick with a magnet and became transformer, right? So that is helping you to remember the 4 drawers. The first drawer is current carrying conductor, force on a current carrying conductor. Second drawer is electric motor. Third drawer is electromagnetic induction, and fourth drawer is transformer. So I think you can easily associate why this story is being created and how this story is able to help you to remember the name of the 4 drawers. And that's AI animated video. The first few seconds is helping you to remember this story even better because it's an animation, right? So we have already read this chapter, step 2 for drawer 1 until drawer 4. We will continue on step 3. Now, step 3 is to build your level of understanding from level 2 to level 3. For Singling, you should be at level 2 now. For Aiden, you need to catch up a bit to be on level 2, and now we are going into level 3, right? Like I say, if you read all these Faraday's law, you read all these Fleming left-hand rules, for now, if you don't understand fully, that is fine. So do not set a high expectation for yourself and be so anxious throughout this 2 hours journey, right? So you just need to know there is something called Fleming. You just need to know that the Fleming is having a rule that is involving left hand and also right hand, right? Left hand is on the drawer 1, right hand is on the drawer 2, okay? And that's it, because we are still at level 2. We are not at level 10 or level 9, okay? So don't expect yourself to remember, to understand what you have read just now, right? And this is 3. Okay, so let's start with step 3. We'll go from drawer 1. You see the format is also the same. You have a catapult field here, and you have a catapult field here. And it's an extension of what you have read here in just 1 or 2 lines. And obviously with that, you are able to increase your knowledge about what is in drawer 1 to help you to level up from level 2 to level 3, right? So let's start from drawer 1 until until here for 1 minute. For 2 minutes, I'm going to scroll down as we go. All right, let's start now. Start drawer 1. I'm going to scroll down a bit more later. This chapter is not an easy chapter, just to let you know. Okay, by now you should be reading the diagram and appreciating what is the magnetic field, what is catapult, how the magnet affect it, and what is the force. All right, time's up. Okay, I'm sure after reading this, if it is the first time you read this chapter, you have almost no idea, or next to no idea, not zero, but maybe a little bit, only a little bit of understanding of what you have read, and that is fine, right? Because as I told you just now, this chapter is not an easy chapter. You need to have a bit more of imagination on the interaction between the magnet, which is this north and south magnet, and this is the magnetic field. And then what is this? This is the conductor. Conductor is like a copper, right? And that is having this electricity current, and that is also creating another magnetic field, right? So that's being labeled over here. Magnetic field from current carrying conductor. So imagine a copper that is having current, that's having electricity on it, and it will have magnetic field. And how is it interact with the magnetic field that is between these two magnets? And this is how they interact, right? So you just need to know there's some interactions, right, for now, because now we are building your understanding from level 2 to level 3 for drawer 1. Okay, so let's read this 1.2 until together in 1 minute. 1 minute. Let's do 1 minute. Okay, time's up. So by now, at level 3 for drawer 1, you should be having some idea, very not full, okay, but some idea that there is this forces between the current carrying conductor and also magnet and the magnetic field, is one is being interacted. There is some forces that is being applied over here, right? And that force, how do we determine that force? Is using these rules, these new rules that you read just now, Fleming left-hand rules, right? So there are these 3 fingers, okay? How this is being relayed to your fingers, we'll have more information later. If you do not fully understand it by now, it's fine. You just need to know there's a Fleming left-hand rules to help you to determine the force, which is using the thumb. Then to help you to determine you have to set the index finger which directions. If the north is here or the north is here, then the middle finger is having showing the direction of the current from positive to negative, the current of the conductor. Okay, now let's move to drawer 2. Drawer 2 is here, working principle, speed factor, brushless, and brush the motors. So let's start with 2.1 working principle, right? We'll do, okay, it's not too much from this drawer 2. Let's combine them together, right, like this. So we'll do 2 minutes from drawer 2 until here, the coil. Let's start now. 2 minutes. All right, time's up. This is drawer 2, which is electric motor. The name is electric motor. Electric motor means what? Means you are converting the electrical energy into a kinetic energy. What is the most common application that we have in our house that is using electric motor? The fan, right? The fan, when it's so hot in your room, you turn on the fan. You turn on the fan. Once you turn on the fan, that means it is converting electric into kinetic energy to move the blade of the fan so that it will generate wind to cool down the room temperature, right? So that is electric motor. And how it works, this is the principle of the DC motor, right? And the DC motor, there are 2 types of motor, brush motor or brushless motor. Brushless is the more advanced one, the newer one, right? Brush is before the brushless, right? And they have pros and cons. Mainly the brushless is the more advanced. That means having more advantages compared to the brush motor, right? So there are links over here to help you to understand more details on what is brush motor, what is brushless motor, and what is the working principle of DC motor. right? And then factor affecting it. I find it not too easy to understand by just reading it. That's why I search from YouTube on the link and put it over here to help you to understand it after hoping that you are after watching this you are able to understand it better, right? But for now, we will not watch the video. We will continue. We will continue. You can come back to this link if you think that you did not understand the principle of the motor and you need more information about the brush and brushless motor later. Okay, but for now, let's continue on the steps. And drawer 2, step 3 is done. So your understanding level should increase to level 3 now. Level 3 is still a very low level. That means you just need to get 3 out of 10 correct MCQ if you have to put it into MCQ. And that is fine if you get 3, right? So don't over expect yourself to understand everything for now. Okay, this is also okay. We'll divide it into 2 sections. So let's start now for 1 minute. Drawer 3 until motion. Okay, time's up. I'm not sure whether it is too short. Okay, let's do another 30 seconds. Let's do another 30 seconds. Okay, so it's introducing 2 laws, 2 fundamental laws, Faraday law and Lenz's law. What are those 2 laws? This is the explanation. This is the explanation, right? If you need a short summary, this is the short summary. This is a short summary about the 2, the Faraday's law, right? Lenz's law is not written over here. It's written over here. Point number 2. Okay, so Lenz's law is something related to the solenoid, and it's to always oppose the change of magnetic flux. If you cannot imagine this by now, it's fine. We're going to go through it as we go along the steps. But you need to know that there is something about Lenz's law and Faraday's law that is in drawer 3. Okay? And there are some factors that's affecting the strength of the Faraday's law and also Lenz's law. Okay? This is the Lenz's law. This is the Lenz's law. Let's take 1 minute to appreciate this picture. I think that's the explanation, yeah. So the picture, only the picture, 1 minute. The 3.2, we'll do it late. We'll do it in another timeline. Okay, 10 more seconds. Okay, don't be frustrated if you do not fully understand it. That is fine, because as I said, this chapter is not an easy chapter. So I'll explain briefly what is this. You have A, B, C, D. This is the solenoid, right? This is the whole thing is a solenoid with the north and south, with the cable and the voltmeter. And this magnet, if it is going into these directions, then the N changes. The pole of the solenoid changes, right? So if you can compare, what is the difference here is the direction of the current, and also the pole of the magnet of the solenoid changes based on the permanent magnet. This blue and red color is a permanent magnet, the direction of the permanent magnet into the solenoid. Into the solenoid. Solenoid here this is like a hole. You can push this magnet into this bar. It's a hole here, right? It's not a solid, like a space. There's a space in between here. You can push it or pull it out into it. Right. I hope this is helping to explain for drawer 3. Oh yes, what's the difference between drawer 3 and drawer 2? Drawer 3 is using magnet to generate electricity. Okay. Drawer 2 is using electricity to generate movement, kinetic energy. So drawer 3 is using movement of the magnet to generate electricity. Okay, I repeat, drawer 3 is using movement, because if you move this magnet in and out, that means what? There's movement. And then there will be electricity that's being generated. So there will be current that's flowing in this wire. For drawer 2, you are using electricity that you plug into your, you get from your battery, or you get from your power source from your on your wall, right? And get movement. That means it's like a blade of the fan that is moving. All right. Now, so 3.2 until this table, we'll do 2 minutes. Let's start now. Okay, time's up. Excuse me. Why is this chapter is not as easy as other chapter? Is because it requires you to imagine and to see how the mechanism of the generator or how the electric mechanism of the motor. So far now you are reading from text. Text, if you are able to imagine, if you are the student that is having a very high creativity, and by reading this, you are able to imagine the generator, how they move, and imagine the electric motor, how they move, then excellent. This is good for you. But not all the students are like that. I think most of the students are not like that, where just reading the text, you are able to imagine the motor, right? So that's the reason why I say this chapter is not as easy as other chapters, right? So let's continue. Let's continue and see as we go along whether you are able to understand better, right? If not, you can still come back to read and also read from the books, because book has more pictures and diagrams to help you to imagine, right? So for drawer number 4, excuse me, drawer number 4 is transformer. We will do, let's do 2 minutes from drawer number 4 transformer 4.1 until 4.2, right? 4.3, we will leave it for another part. Let's start now. Okay, 20 seconds. The formulas look scary at first, but it's not as scary as you think. All right, so let's continue on the last part here, 4.3 for 1 minute. Let's start now. You can read first while I'm checking, configuring the timer. All right, now we've completed step 3 for drawer 1 until drawer 4. and what we should be expecting. Our level of understanding should be at level 3 now. Now we are moving into level 4. We're moving into level 4. So let's do a quick recap. Let's see. Now we have this drawer, 4 drawers, and also we have this AI, we have this story, and we have AI animated story to help you to remember this story easily, to be link it with the name of the 4 drawers, right? So let's take 1 minute to read from drawer 1 until eddy current. And I need you to have this feeling that 15 minutes ago, when you first read it, you have you don't understand fully what is it. But now 15 minutes later, you should have more understanding. Not full understanding, but more understanding. Once you have that feeling, then it's fine. Let's start now. Let's read this. Step 2 until eddy current. Ten more seconds. All right, let's cut it now and time's up. Right. So what I need here is I need you to have this feeling, the feeling of you understood a bit more compared to 15 minutes ago when you started reading step 2 without step 3. Now, after step 3 and read back, and what now you're reading back step 2, you should have a better feeling that you understand it more, not full, but more. Okay. So it's the same feeling I want you to apply after reading or after working on step 4. Right. So what you need to set your expectation right now here is you need to move the level of understanding from 3 to 4 after reading this. After reading this, right, which is drawer 1. Okay, let's get 1 minute to read this. Start now. 1.5 minutes. I think it's a bit too long for 1 minute. Too short for 1 minute. Okay, I'll start again. So now 1 minute. So total 1.5 minute. Ten seconds. All right. Drawer 1, you have 2 questions, FAQ 1 and FAQ 2. So if we need to put it into numbers in your understanding level, you should be at 3.5. Okay, 3.5. So after going through or reading this FAQ 2, you should be level 4 for drawer 1. Okay, let's do 1 minute for question 2. If you finish reading question 2, then you can continue. You can read question 1, reread question 1 again. Ten more seconds. All right. So I hope you learned something new on drawer 1 to help you to improve your understanding from level 2 to level 3 to level 4. Right. So we are also having two FAQ for drawer 2. So let's do FAQ number 1 for 1 minute. Let's start now. Okay, time's up. Let's go for question 2 to improve your understanding to level 4 for drawer 2. Start now. Okay, time's up. Now let's move to drawer 3. Drawer 3 is electromagnetic induction. Right, the magnet. In the story, remember the magnet that stick on the electric motor of the conductor. So that's the magnet. So let's do 1 minute for question 1. Start now. Okay, let's do question 2 for 1 minute. If you have extra time, then you can read question 1 again if you want. Let's start now. All right, 5 seconds. Okay, let's move on. For drawer 4, we'll do the same thing, 1 minute and 1 minute. Let's start now. Okay, let's go for question 2. If you haven't yet, another 1 minute. Let's start now. Okay, right. Now we are going to step 5. Right, step 5 is more information, or maybe if you read it, if you have two feelings. One is step 5, the content of step 5, some of them you have already read it before. So that is to reinforce your understanding on this particular drawer. For this case, will be drawer 1. If you see new information, that means that is the new information that maybe you missed it in the previous steps. Right. So step 5 is having information that was in step 3 and step 4. If you read it now in step 5 and you are able to identify that this is something that you have read, then it's fine, and that is good. If you see that it's a new thing, that means maybe you have already missed it in the previous steps, and now it's a new information for you. Then let's capture that into your understanding to level up your understanding from now level 4 to level 5. Level 5 is 50%, right? 50%. So we are increasing it slowly. Now, how we are going to do this? I'm going to give you 2 minutes to read from step 5 until aircraft. I think 3 minutes, okay? Step 5 until aircraft. I'm going to scroll down as we read. 3 minutes. Let's start now. 1 more minute. Okay, time's up. Let me find how the Fleming rules looks like. The Fleming fingers. Wait, let me just open the textbook. Okay, this is the textbook. See, this is your finger. This is Fleming left-hand rules, right? So if you compare this, your left hand, you do it like this, perpendicular to each other, these three fingers. What does it represent? If you compare it to this magnet and this current flowing on this conductor, right? So this is the current, the direction of the current from positive to negative. Then the magnetic field from north to south, right? And then what happened? There's a force that's being created. Remember, we're trying to create kinetic energy, from electric energy to kinetic energy. So the electric energy, which is this current, once it's being conducted, once the current being started to flow, then there's a force that's being created. And that force is going up or going down? It's going up based on your thumb finger, right? Now, let's say now the north and the south change place. So north is here, south is here, but the current is still this way. Then you have to turn your fingers another way, or turn your entire hand another way. That means this index finger need to be pointing into opposite direction. Then what does it mean? That means your thumb now is pointing down, right? And if your thumb is pointing down, that means the force is going down. The force is going down. Force of what? Force of the push, to push the conductor or this conductor down or up. Okay. I hope this gives a bit more clarity, because as I say, this chapter needs you to appreciate the mechanism of the motor or of the electromagnetic inductor. So just by reading text, maybe it's a bit difficult to be imagining the mechanism, right? Okay, drawer 2, we'll do 3 minutes. Let's start now. The intention is to move from level 4 to level 5 of your understanding. 2 more minutes. Let me scroll down a bit. Okay, lifespan is the last. Okay, the DC motor is also quite difficult to understand by just reading it. Even it is, if I put it on the screen, on the picture, it's also not that easy to understand by just reading the diagram. Right, even with diagram, it's not easy to understand how the mechanism works. Let's do this. I'm going to this drawer 2. I'm going to go up. Remember, there are a few YouTube links that I attached. Let's see if I can find them. This drawer 3. Yes, drawer 2. You see drawer 2? We have a few YouTube links. And let's watch one YouTube link. It is about 10 minutes. Okay, let's do that. 10 minutes. Let me just open it.
If you look around your house, you will see many devices that have electric motors, such as kids' toys, table fans.
Okay, if you are not able to watch it or listen, let me know. I'm going to continue to play for 10 minutes.
Toothbrushes, hair dryers, and this electric cutting knife. But how does the electric motor work? You turn it on and somehow it starts rotating. Why is that? In this video, we'll cover the basics of electricity and magnets, and then put it all together to understand how the motor works. This video is sponsored by Brilliant. Let's start with something called a circuit. You have a battery, some wires, and a device that uses electricity such as a light bulb. Electricity flows through the circuit, but as soon as there is a break in the wire, the electricity stops flowing and the light bulb goes off. The path must be complete for the circuit to work. This is best done through the use of a switch. Electricity is flowing down the wire. This is called conventional flow. If we take the battery out and flip it, then the current will flow. The light bulb will still work in either case, but there are some devices that will work differently depending on which way the current flows. Okay, so that's the basics of a circuit. Now let's come over here. This is a magnet. It has a north pole and a south pole, and it likes to attract other metal objects like these paper clips. If you bring another magnet towards it, opposite poles attract, and the same poles repel. Magnets don't have to be in this shape. For example, some magnets might be more flat like this. You can think of this magnet as always on. It's always working. You can't really turn it off. That's why it's sometimes called a permanent magnet. It's made up of many smaller magnetic domains that are lined up in the same direction. But later I'll show you a type of magnet where this is not always the case. Let's take one of our permanent magnets and drill a hole in the center and put it on something that will allow it to spin. Now bring another magnet towards it. Our spinning magnet will immediately line up until opposite poles are right next to each other. Now switch out the side magnet. The same poles repel and opposite poles attract. If we keep switching out these side magnets, then our spinning magnet will just keep spinning. This concept of the spinning magnet is really important. We'll come back to it in a moment. Here's a metal bolt which is not a magnet. It's made up of magnetic domains, but they are pointing in random directions. Now let's take a wire, wrap it around several times, and then create a circuit. The current through the wires forces the magnetic domains to line up. That means we've just made a magnet, or more specifically, an electromagnet. It can do the same things that a permanent magnet can. It can pick up pieces of metal, and it has a north and a south pole which will attract or repel other magnets. But the electromagnet is special in the sense that it can be turned on or off, just like the light bulb. You can't do that with a permanent magnet. Now watch what happens when we flip the battery. The electric current was flowing this way, but now it flows the other way. This will cause the poles on our magnet to switch places. North will become south, and south will become north. This is called reversing the polarity of an electromagnet. Instead of flipping the battery, an easier way to do this is to just switch the wires. You should be aware that the electromagnet will get very hot if it's on for a while. Just a caution in case this video inspires any science projects. Let's come back to our spinning magnet. This time we'll replace the spinning magnet with our electromagnet. As soon as we connect the wires, the magnet turns on and it lines up with the side magnet. Now in reality, connecting these wires would prevent the bolt from spinning freely, but what's important here is the concept of the spinning electromagnet. Now let's switch the wires to reverse the poles on the electromagnet. The same poles repel and opposite poles attract. Now reverse the polarity again. Same poles repel and opposite poles attract. If we keep switching the polarity, our electromagnet will just keep spinning. To make this stronger, let's bring in another permanent magnet on the side. Notice how this side has the south pole towards the center, and this side has the north pole towards the center. The side magnets work together to spin the one in the middle. This right here shows the very basics of an electric motor, but we need to make a few improvements. The two side magnets can be replaced with stronger curved magnets. And instead of a bolt with wires, we're going to use a metal loop. This is called the armature. Connect our wires and we have a circuit again. This time you can think of the electromagnet as flat like this with the south pole pointing up. Now the armature will spin until opposite poles are lined up. We can keep it spinning by switching the wires just like we did before. But this is a lot of work to sit here and manually switch these wires. We need to add something to the armature called a commutator. It's a ring with gaps on the opposite sides. The commutator will spin along with the armature. Now we connect the circuit with two brushes on the side. These brushes will slide along as the commutator spins, and they are spring-loaded so that they always maintain contact. The current flows from the wire, through the brush, the commutator ring, the armature loop, and back through the other side. Now we have our electromagnet and the armature spins. As we come around this time, the brushes will switch contact to the other side of the commutator ring. Remember, there's two brushes, so this is happening on both sides. Before the switch, the current in the armature is flowing this way. After the brushes switch sides, current will flow the other way. This means the electromagnet switches polarity, which will cause the armature to keep spinning. This commutator ring does the same thing as switching the wires like we were doing before, but this time it does it all on its own. It will spin as long as we're connected to a battery. Disconnect the battery, no more electromagnet, and the spinning stops. Now so far we've only used one loop on the armature. This will cause our motor to have an irregular speed, and in fact, we could get stuck in this position, with the brushes halfway between commutator segments. What we can do is split the commutator ring and then add another loop. So first, the brushes are in contact with these two commutator segments, which turns on this electromagnet, which causes it to start spinning. Once we get to here, the brushes switch contact to the next pair of commutator segments, which means this loop turns off and the next loop turns on. Now this electromagnet wants to spin. The brushes switch contact and the next loop turns on. This keeps happening as our motor spins. It's almost like the loops will take turns being an electromagnet. Some electric motors will add many loops to the armature. This ensures that there will be a continuous spinning motion on the motor. This spinning force on the armature is called a torque. Stronger torque means a faster spin. There are some things we can do to improve the torque of the motor. Electromagnets are stronger when there are more wires. This is true when we wrap more wires around the metal bolt, and it's also true when each of our armature loops are made of many wires. The motor will have stronger electromagnets, which means it will spin faster. If you look at some pictures of real electric motors, you can see lots of wires wrapped around. And yes, this is the same reason. More wires wrapped around means stronger electromagnets. Another way to make this stronger is to use more electricity. Let's learn a few more terms here. The part that doesn't move is called the stator. In this case, it's the two permanent magnets on the side. These fit inside the edges of the motor case. The armature in the middle is also called a rotor. Remember, this is the part that spins. The axle goes through the middle here and then sticks out the back of the motor. What I've shown you in this video is called a DC motor. If you have a device that moves and is powered by a battery, there's a good chance there's a DC motor in it. Other types of electric motors will work a little differently than what I've shown here. No matter the type of motor, most of them will produce some type of spinning motion. Once it's spinning, we can use this to make different devices move. In this case, a kid's toy. Or even a fan that cools your room. The spinning of the motor can be converted to other types of movement, such as the side-to-side motion that we see in this fan. Or how about this electric cutting knife? Each blade is going back and forth. It all starts with the spinning of the motor to turn a gear, which then pushes these two pieces back and forth. So hopefully this video has made a few light bulbs go off in your brain. If you like learning new things, head on over to Brilliant.
All right. I hope this explains a bit more detail and clear a bit more gaps that you have. Now, let's continue our journey on step 5. We finished step 4 for drawer 3, right? So drawer 1 and drawer 2 are done. And now going to drawer 3. Drawer 3 is electromagnetic inductions. We will do 3 minutes for drawer 3. Let's start now. Okay, let's scroll down a bit to cover the lower part. One more minute. And then the hardest part is done. 30 more seconds. Ten more seconds. All right. Okay. So let's continue on drawer 4, the last drawer. We'll do also 3 minutes. Let's start now. I'll slow down a bit. Thirty seconds. Okay. So this resistance for this particular for this part where you have resistance of coil, eddy current, hysteresis, and leakage of magnetic flux. This is to increase the efficiency of the transformer and to manage the energy loss. So there are 4 key factors. Right, we're going to create a story, a small story for these key factors. Right, for example, later in the step 6, which is next here, you have this. Let's focus on this part, the last part of draw number 4. Real eddy have a leak. So real, the R is resistance, eddy is the eddy current, have a leak, have is hysteresis, leak is leakage of magnetic flux. Right. So real eddy is not a fake eddy. He went to the toilet to pee. So real eddy have a leak. You can think of it this way. Right. So that is for this part here. Then now let's move to step 6. Step 6 is having each story for each drawer, right? So I'll tell you my story that can help me to remember what is in drawer 1. Okay, so let's look at this step 2 as a reference. In drawer 1, you have these informations, this key information. You have catapult field, you have Fleming left-hand rules, you have the factor that is affecting it, right? So what is the story that I've created? I've created Fleming here. If you look at here, this is the story. So you have the drawer 1, the drawer 1 name, and then you have drawer 1 story. Fleming uses left-hand launch catapult into strong magnet. So what does it mean? So you can already, I think, by now, to link it why I created this story. So Fleming using left hand, that means this talking about left hand rules. So this will help you to tell you, to remind you that this drawer is having something related to Fleming left hand, right? Then obviously it's the Fleming left hand rules. Then when you think about Fleming left hand rules, you think about your thumb, your index finger, and your middle finger, right? And why you need that? Because you need to determine the direction of the force or the motion, right? The picture that I show you a while ago, right? So launches use his left hand and launches a catapult, right? You know, catapult is the you're gonna see that in the animations, right? When during the ancient time, when they fight against each other, they have this catapult that's launched to attack the castle, to destroy the castle, right? So this sounds like the catapult that we are learning as a catapult field, right? Then into a strong magnet. Into a strong magnet is to relate to this factor that is affecting the force. Larger current or stronger magnet, right? Stronger magnet into a strong magnet. So this very short story is already able to help you to know what is inside drawer 1, right? What is inside drawer 1, okay? So now drawer 2, a witch turn electric plus magnet into movement, right? Then she commutes on her toothbrush, right? I think these keywords itself already is by now you know is in the drawer 2, right? So a witch turns Alakadabar, turns the electric and magnet into movement, right? So they make it the movement from the electric and magnet. You can see in the animations the witch is doing that. So this will help you to remember this electric motor there's something related to the electric, and it is something related to the magnet, and something related to the movement. Movement is the force, right? Then she commutes on toothbrush. So there is this ring split commutator, and also the brushless and brush motors, right? Of course, we are not talking about the toothbrush, but we are using the toothbrush, the brush terms to help you to remember that there is something related to brush in drawer 2, right? In drawer 2, okay? Drawer 3, electromagnetic induction. So on Friday, lens turns motion plus magnet into electricity, right? So the difference over here between drawer 3 and drawer 2 is now drawer 3 is using motion and magnet and then create or generate electricity. For drawer 2, you are using electric plus magnet to generate movement. Okay? So there are two different mechanisms in two different drawers, I would say, right? That's why they are in two different drawers. So on Friday obviously we are talking about the Faraday, right? To help you to remember, there is this Faraday law, right? Just to create these terms called Friday. And this lens is Mr. Lens, okay, whoever it is, there's the guy named called Lens on Friday. He turns motion and magnet into electricity, right? So Lenz is the Lenz law, right? Related to the solenoid, related to the opposite, oppose the changes in magnetic flux, right? Then they are also having Fleming, but now this time they're using right hand, okay? Right hand. So Fleming turns the right fast knife cutter, right? Not the wrong one, the right one. And it is fast knife cutter, but on an opposite direction, right? So Fleming turns on the right fast nail cutter on the opposite direction. So this right is to relate to right hand. Fast knife cutter is to relate to the faster you cut the magnetic field, the bigger electricity you're going to generate, right? And then opposite direction. The opposite direction is talking about the Lenz law, opposite direction. Okay? So drawer 4, big transformer step down to small. All right, so there's a big transformer, the one that you see in the cartoon. He stepped down and then becomes small. Right? This is to explain how the transformer works. Right? Why transformer need to step up and step down? I think by now you should know. Right? If not, then later in the video, we are going to tell you also. In the video of step 7, not this video, not this animation video. Step 7, there's another video. Yeah, step 7, if I scroll down, that's step 7, there's another video. It will also explain a bit more on why step up and step down. Even in the quiz, they will give you a bit more information. Okay? Now, real eddy have a leak, we explained just now. Resistant, eddy current, hysteresis, and leakage. Right? So now, this video, we can play it very quickly. Okay, we can play it very quickly.
Form 5, Chapter 4. Electromagnetism. You force current train. Conductor, ride, electric motorcycle. That stick, a magnet, and B, transformer. Draw
Okay,
1.
now we are going into each drawers, and each drawer is having their own story, which I explained just now, to help us to remember what is in each of the drawer.
Force on, current carrying conductor. Fleming uses left hand. Launch catapult into strong magnet. Draw 2. Electric motor, which turn electric plus magnet into movement. She commute on her toothbrush. Draw 3. Electromagnetic, induction. On Friday, Lenz turns motion, plus magnet into electricity. Fleming turns on the right fast knife. Cutter, but opposite direction. Draw 4. Transformer. Big transformer step, down to small. Real eddy hat to leak.
Okay. I hope by now, when you watch the animation just now, it gives you a bit more context, a bit more understanding, right? Why this animation is created that way, right? Remember, 1 hour ago, when you watched this video, probably you do not have an idea why is this like this. But now, with us going through from step 1 right until step 6, you should have a clearer idea of the animations, right? And that animation is to help you to remember the story easier, right? This is the picture of each of the story, but that animation is going to help you better, right? But when you're going into exam, you cannot bring the animation into the exam. You cannot bring your phone with the YouTube link to help you to remember what is inside which drawer. This is how you are able to help you to remember. You can draw in the exam, I believe, okay? You can take an empty paper from the examiner and you can draw it out. Once you draw it out, I think immediately this will help you to refresh what is the story for drawer 1, drawer 2, drawer 3, and drawer 4. Right, let's talk about drawer 1. Let's see. See, this is the Mr. Fleming. He used catapult and throw it into a big magnet, a strong and big magnet. Right, what does it mean? So drawer 1 is talking about something related to Fleming left-hand rule, still left hand. And there's something related to catapult field. And there's something related to strong magnet. Okay? Same goes to the rest, right? There's a witch chain turning the electric and magnet into a movement, right? And then she travel on this commute is a keyword, on this toothbrush, right? So those keywords will help you to remember what you have learned in this drawer, right? Same goes to drawer 3, same goes to drawer 4, transformer, right? Okay, so I think we are done with the step 6. So let's move to step 7, right? Step 7. Step 7 is this quiz. So we have 10 quiz. Is it 10 or 8? Yeah, we have 10. Okay. So we'll do quickly on this. How do we do this? I hope you still remember. When you read the questions, you ask yourself, which drawer is this? Obviously, this is drawer number 1, but the intention of asking yourself help you to reinforce the drawer name that you need to remember, right? Then you create your own answer before you read the answer, right? And then take your answer and take this answer that is being provided and compare between these two. If there's nothing new, then you are reinforcing your learning. If there's something new, then you are taking this new information and put it inside your brain drawer, right? And now the objective here is to increase your level of understanding from 6 to 7. 7 is a good level, right? You should be able to understand this well. So let's take 1 minute to read, and 1 minute. Sorry, let me just do this first. Do this right first. So let's take 1 minute to read, and then form your answer, and then compare it with the answer that you have here. 1, 2, start. Okay, time's up. We'll do the same thing for question 2 and 3. Okay, 1 minute, 2 and 3. 2 is drawer 1, 3 is drawer 2. Let's start now. 1 minute. Okay, now let me re-emphasize again. When you read the question, I know it's very tempting to just read the answer, but make it a point, because it's for your own benefit. Before you read the answer, read the question, then form some answers that you can form for these questions. Once you have formed that very quickly, about like, I don't know, like 5-10 seconds, then only you read the answer. Okay. You can use this step 2 as a reference on the answer that you want to create before you read the answer. Okay. So let's do 1 minute for question 4 and 5. Start now. All right. Now we are going to question 6 and 7. Let's do the same exercise. Right. But like I say, do your own answer first before you read the answer. Let's start now. Okay. Let's do question 8. 8 and 9, 1 minute. 8, 9, 10, 2 minutes. Let's start now. 8, 9, 10, 2 minutes. Oops, sorry. 1 more minute. Okay. Now we are done. This is the easiest part, step 8 and step 9, which is to watch the video. I don't know whether you are having this feeling after, not for this chapter, but for the previous chapter. After you watch the video for this step 8 video, most of the puzzle now puzzle together. That means your understanding of the entire chapter suddenly went up to a higher level, right? I don't know whether you have this feeling. I hope you do, right? Why? Because this video is explaining to you step by steps from drawer 1 until drawer 4 what you need to know in each of the drawer, right? And when you're watching this video, you've already gone through from step 1 until step 7. So all the new terms, new concept, new principle that you are struggling to understand as you move from step 1 until step 7, in step 8, it puzzle in or puzzle out or placing all this puzzle together for you. That is the reason why you have this sudden feeling that after watching this video, everything seems to be clearer. Okay, let's see whether this is still the case. After watching this video, let's turn on this video, the 9 minutes video.
Hey everyone, welcome.
Okay, so let's see whether you still have the same feeling like what you did for the previous few chapters after watching this video for this 9 minutes video. Let's start now.
Today we're going to pull back the curtain on one of the most fundamental forces in the universe, something that's all around us, powering our entire world, but is completely invisible. We are talking about electromagnetism. It's the engine behind just about every piece of tech you can think of. So let's dive right in. So to get us started, let me ask you something. Think about an electric car, silently gliding down the street. Then picture a giant wind turbine, its blades turning slowly in the wind. And then just think about that simple little charger you plug your phone into every single night. I mean, on the surface, they couldn't be more different, right? But they all share one incredible fundamental secret. Yup, that's it. It all comes down to electromagnetism. Every single one of them works because of this amazing dance between electricity and magnetism. So in this explainer, we're going to break down the 4 key building blocks of how this all works, starting with just a simple force and building all the way up to our global power grid. All right, so let's start at the very beginning, the most basic concept, a physical force. See, when you mix electricity and magnetism in just the right way, you get motion, and it all kicks off with something called the catapult effect. So what on earth is a catapult field? Okay, imagine you've got a regular magnet with its magnetic field. Now let's run a wire with electric current flowing through it, right through that field. Well, that current creates its own little magnetic field. And here's the cool part. Where those two fields line up, they get stronger together. Where they oppose each other, they get weaker. And since nature loves balance, the wire gets physically shoved from that strong area into the weak one. That push, that shove, that's the force we're talking about. Okay, so how can they possibly predict which way that wire is going to move? Well, luckily for us, there's a handy little trick for that, a sort of cheat code, Fleming's left-hand rule. It's super simple. You just take your left hand, point your first finger in the direction of the magnetic field, then point your middle finger in the direction of the current, and bam, your thumb magically points in the exact direction of the force. It's a pretty brilliant way to see this invisible interaction, right? So what if we want to make that push that force even stronger? Well, it's pretty straightforward. You have 2 main options. You can either crank up the current flowing through the wire, or you can just get a much stronger magnet. Either way, you're beefing up that interaction between the 2 fields, and the result is a much bigger, much more powerful push. Okay, a single push is cool and all, but the real magic happens when we turn that one-time push into continuous, non-stop rotation.
Drawer 2.
That brings us to our next building block, and it's something you use every day, the electric motor. An electric motor is basically a machine that's built to perfectly master that catapult effect. It takes in electrical energy, and using that very same force we just talked about on a coil of wire, it converts it into kinetic energy. Or, in simpler terms, movement. Pure, powerful rotation. But here is the really ingenious part. How does it keep spinning? Because after that first push, you'd think the coil would just stop. Well, the secret is a clever little device called the commutator. Think of it as a split ring that acts like an automatic switch. Every single time the coil makes half a turn, the commutator flips the direction of the current. This reverses the push on each side of the coil, giving it another kick in the same direction. It's just push, flip, and that's how you get that smooth, continuous spin. And this technology has gotten so much smarter over the years. You see, in the old school brushed motors, the coil spins and these little physical carbon brushes literally rub against the commutator. This causes friction, noise, and eventually they wear out. But in modern brushless motors, some genius decided to flip the whole design on its head. The coil stays still and the magnet rotates around it. This gets rid of all those parts that wear out, which means the motor is way more durable, a lot quieter, and much more efficient. It's a huge reason why things like electric cars and drones are so powerful today. Okay, so far we've seen how electricity plus magnetism equals motion. It's a pretty solid formula. But what happens if we flip that entire idea around? What if we start with the motion first? This right here is the question that literally changed the course of human history. If we can use a current inside a magnetic field to make something move, can we take that movement, put it inside a magnetic field, and create a current? And the answer is a massive, world-changing yes. And this incredible phenomenon is called electromagnetic induction. To put it simply, anytime you move a wire through a magnetic field or move a magnet near a wire, it works both ways, you generate a voltage in that wire. Physicists call it an electromotive force, or EMF, and if that wire is part of a complete circuit, an electric current just starts to flow. No battery required. All you need is motion. Now, there are two big rules that control how this works. First, you've got Faraday's law. This one tells you how much voltage you're going to get. Basically, the faster you cut through those magnetic field lines, the more juice you generate. Then you have Lenz's law, which is kind of weird. It tells you the direction of the current, and it's a bit of a rebel. The current always flows in a direction that creates its own magnetic field to fight back against the original motion. It's like nature's own little system of checks and balances. And guess what? Just like we had a rule for motors, we've got one for generators too. But this time, you need your right hand. It works almost the same way. Your first finger is still the magnetic field, but now your thumb represents the direction of motion, the force you're applying, and your middle finger will then show you the direction of the current that you've just created out of thin air. This very principle is the beating heart of every single electric generator on the planet. A DC generator uses that same clever split ring commutator we saw in the motor to make sure the current always flows in one direction. An AC generator, though, uses much simpler slip rings. This lets the current naturally flip its direction every half turn, creating the alternating current, or AC, that powers pretty much all of our homes and cities. So we can create force, we can create rotation, and now we can generate our own electricity. We're almost there. The final piece of this giant puzzle is, how do we move all that power around efficiently? Well, that's where the transformer comes in. Here's the big problem that transformers were invented to solve. If you try to send a huge amount of electrical current through hundreds of miles of power lines, you lose a ton of energy along the way. The resistance in the wires just turns that precious electricity into wasted heat. It's incredibly inefficient. And the solution is just so elegant. A transformer uses that same principle of electromagnetic induction we just learned, but with a twist. There are no moving parts. It's all done with magnetism. An alternating current flows into a primary coil, creating a magnetic field that's constantly changing. A soft iron core then guides that changing magnetic field over to a second coil, and, just like with the generator, it induces a brand new voltage. It's a way to pass one circuit to another without them ever touching. And here's the really cool trick. It all depends on the number of turns of wire in the coils. If the second coil has more turns than the first one, it becomes a step-up transformer, and the voltage gets a huge boost. If it has fewer turns, it's a step-down transformer, and the voltage is reduced. More turns, more volts. Fewer turns, fewer volts. It's that simple. And it's how our power grid can step up voltage to travel long distances efficiently, and then step it down to a safe level right before it gets to your house. Now, no machine is perfect, but modern transformers are astonishingly good at their job. I mean, they can be up to 99% efficient. Think about that for a second. That means almost no energy is lost when we're changing the voltage. But that last 1%, well, engineers are always trying to get that back. So how do they chase that last little bit of efficiency? Well, it's a whole series of clever engineering hacks. To fight the resistance in the coils, they just use thicker copper wire.
To stop these weird little whirlpools of current called eddy currents from heating up the core, they build the core out of super thin insulated layers. They even use soft iron because it's easy to magnetize and demagnetize, which saves energy. It's really a masterclass in fighting tiny energy losses.
And that really brings us full circle, doesn't it? From that simple initial force on a wire, to the motor that uses that force to spin, to the generator that spins to create power, and finally to the transformer that delivers that power to us. It really is all one beautiful interconnected system, all built on these elegant rules of electromagnetism. This invisible force has completely built our modern world, from the power plants that light our cities to the very device you're using to watch this right now. The real question is, as we get even better at understanding and using these principles, what will electromagnetism power next? Thanks for watching.
All right. I hope you have the feeling that suddenly puzzle up together and help you to move from level 7 to level 8 now, right? So level 8. So let's go for the last one. And what should you be expecting? This podcast, after listening to it, it is reinforcing what you have learned just now or what you have watched just now with the video, right? So let's see how long is this.
Picture a
Okay,
300
6 minutes. Okay, Aiden, thank you for coming. We will continue here. Bye-bye.
Picture a 300-foot drop tower ride at a theme park. You're plunging toward the earth, and the only thing stopping you from hitting the ground isn't a mechanical brake,
Right.
but like a ghost.
Right, an invisible magnetic wall.
Exactly. Welcome to this deep dive into the hidden physics of our modern world. Today, we are pulling from a stack of physics texts and technical notes to take you on a logical journey.
Yeah, we're going from the very basic physical shove of a wire inside a magnet all the way to how the alternating current actually reaches your home.
Right. Okay, let's unpack this. Because the thread connecting that theme park brake to your wall outlet is, well, it's just this brilliant sequence of interacting magnetic fields, starting with the catapult field.
Yeah, the force on a current-carrying conductor.
Right. So we know what happens when a wire with current sits inside a magnetic field. It creates its own circular magnetic field, which tangles with the flat magnetic field it's sitting in.
And they literally shove each other. On one side, those field lines stack up and point in the same direction.
Yeah, and on the other side, they oppose each other and cancel out. Think of it like being stuck in a packed, high-pressure crowd at a concert. You naturally just get shoved out into the empty, low-pressure hallway.
The wire gets physically thrown.
Exactly.
What's fascinating here is how we harness that exact hallway shove. If you take that straight wire and, bend it into a continuous coil, the current travels up one side of the loop and down the other.
Oh, so that catapult push goes up on the left and like down on the right?
Exactly. That linear shove becomes a continuous spin. You've just built an electric motor.
Wow. And to keep it spinning in one direction, standard DC motors use a split ring commutator. It's physically just a metal ring cut in half.
Right, and as the coil spins, carbon brushes slide across that gap. They mechanically break and reverse the current every half turn, so the magnetic push stays perfectly timed.
But our sources note a huge shift toward brushless motors now, right?
Yeah.
Because dragging carbon brushes across a spinning metal gap causes, well, a lot of friction and sparking.
Yeah, it's really inefficient. So brushless designs invert the entire architecture. They kept the wire coil completely stationary and spin the permanent magnet instead.
Oh, so you eliminate wear entirely.
Exactly. It vastly boosts efficiency.
Okay, that establishes how pushing a current through a magnetic field creates motion. But the conservation of energy demands a two-way street, right?
Yeah, meaning if you manually force a wire through a magnetic field, the field pushes back on the electrons themselves, inducing a voltage.
Which is electromagnetic induction. Good old Faraday's law. But the critical piece mechanically here is Lenz's law, isn't it?
It is. The moment you induce that current, it generates its own magnetic field. And that new field always flows in a direction that directly opposes the physical motion that created it.
Hold on, so nature is just being inherently stubborn? I mean, it feels like the universe is slamming on the brakes the second you try to generate power.
That's a great way to put it. It's the ultimate toll booth for energy generation. You must input physical, mechanical work to push through that opposing magnetic wall.
Here's where it gets really interesting, though, because engineers use that physical pushback on purpose. Let's go back to that massive drop tower ride.
The magnetic braking.
Yes. Permanent magnets attached to the falling seats drop past stationary copper strips on the tower. The falling magnets induce a massive current in the copper.
And because of Lenz's law, that new current creates its own magnetic field that violently opposes the falling magnets.
Exactly. It safely decelerates the seats without a single moving mechanical brake pad touching. It's just wild.
If we connect this to the bigger picture, though, induction doesn't actually require physical motion. It just requires a changing magnetic field.
Wait, really? We don't have to move the metal.
Right. This is why our grid relies on alternating current. Because AC constantly reverses direction, the magnetic field it creates is constantly swelling and collapsing on its own.
Oh, I see. Which brings us to the transformer.
Exactly. You run AC through a primary wire coil, creating that pulsing magnetic field. You channel that field through a soft iron core into a secondary wire coil.
And because the field is pulsing, it automatically induces a voltage in the second coil. So by just altering the ratio of wire loops between the two, you can step the voltage up for long-distance transmission.
Yeah, and step it down before it blows out your household appliances.
So what does this all mean for efficiency? Because if we are funneling this pulsing magnetic field through a solid iron core, where exactly is the current flowing? Isn't the iron block itself conductive?
It is, yeah. And that is a massive engineering hurdle. That changing field induces mini tornadoes of electricity inside the iron core called eddy currents.
Mini tornadoes. That sounds like a lot of wasted heat.
An enormous amount. So to fight this, engineers build laminated iron cores. Instead of a solid block, they slice the iron into paper-thin sheets coated in insulation.
Oh, so that physically breaks the conductive path. It restricts those eddy currents to tiny localized loops so they can't build up. We literally dissect the iron to trap the current.
That's exactly right.
Wow. We've tracked this from the violent squeeze of the catapult field turning a motor to the stubborn pushback of induction breaking a free fall, straight to the laminated transformers managed.
Okay, I think we're running a bit out of time. Let's do this one, the quick one. Give me an MCQ one by one. Yeah, we'll do one by one. Are you ready, Singling? Draw one. A straight wire carries a current from left to right and is placed a magnetic field directly from north to south. The wire experiences the upward force. Let's do it. Okay, let me pull out this. Yep, let me pull out this here. So what's the answer? Oh, this will be okay, Singling, what's the answer? Uses which rules? Left hand rule, yes. Good. Next one. Still draw one. The student wants to increase the force acting on a current carrying wire placed in the magnetic field. Which change will not increase the force? Increase the current in the wire, use a stronger magnet, increase the length of the wire inside the magnetic field, reduce the current in the wire. What do you think? D, yes. Good. Right? Increase the length doesn't have, okay, let's go straight. Draw one still. Y, okay. Two identical wires are placed in the same magnetic field. Wire X carries a current 2 ampere, wire Y carries a current 4 amperes. Assuming all the factors remain the same, what can be said about the force of wire Y? The force is half of the wire X. The force is the same as wire X. The force is twice, or the force direction is reverse. Okay, good. I think so. Okay, drawer 2. Now we are moving to drawer 2. Electric motor. What is the main function of a split ring commutator in the DC motor? To increase the magnetic field strength, to reverse the current in coil every half rotation, to increase the current flow through the motor, to reduce friction between moving parts. Excellent. Drawer 2 still, okay. A student modifies a DC motor by doubling the number of turns in the coil, replacing the magnet with a stronger magnet. What will most likely happen? The motor rotates slower because resistance increases. The rotate rotates faster because larger turning force is produced. The rotate stops because the magnetic field becomes too strong. The direction of rotation automatically reverses. So number 5. Yes, excellent. 5 more to go. Number 6. Electric motor. A DC motor is running normally. Suddenly, a split ring commutator is replaced with 2 split rings, like those used in AC generator, while everything still remains unchanged. What is most likely to happen? The motor rotates faster. The motor rotates continuously in the same direction. The motor rotates for about half a turn and then turn to reverse direction repetitively. The motor produces electricity instead of rotating. Give a guess. Wrong is fine. It will give you the explanation later. C, that's right. Come on, come on. The AI is still thinking. All right. Okay. So you got it right. Okay. C, a bar magnet is held stationary inside a solenoid. What happens? A continuous current is induced in the solenoid, and induced current flow only when the magnet is moving. An induced current flow because the magnet is inside the solenoid. A large induced current is produced then when the magnet is moving. What do you think? B or D? B or D? Okay, let's try B. Okay. D, a large induced current is produced when the magnet is moving. When the magnet is moving faster, then a larger induced current is produced. Yes, it is correct, but it's not as correct as B. That's why. Okay. Number 8. A student, drawer 3, a student performs 4 experiments using the same solenoid and magnet. Which experiment will produce the largest induced EMF? A move the magnet slowly into the solenoid, move the magnet quickly into the solenoid, hold the magnet stationary inside the solenoid, hold the magnet stationary outside the solenoid. Which one will produce the largest EMF? B. Yep, I think so. 2 more to go. Okay. Still drawer 3. What is drawer 4? Okay. A magnet is pushed towards the solenoid. According to Lenz's law, its induced current will produce a magnetic field that attract approaching magnet, oppose the motion of the approaching magnet, has no effect, reverse the polarity of the magnet. B. I think so. Excellent. Last one. Question 10. Transformer. Transformer has primary coil 200 turns, secondary 1000 turns. Input is 214 volt. Assuming an ideal transformer, what is the output of the voltage? This one is some calculation. Ooh, 10. Number 10. Any answer? You don't know this one. Okay. The answer is C. Let me put D and let's get the explanation. Okay, you remember this scary formula, right? I'll let you read. Okay, I will not read. Once you have done, you let me know. Okay, once you're done, you let me know. Okay, I think you should be done by now. Yes. So clearly you understood everything. Maybe this is your weak spot. I think it's also logical because this one needs to imagine how the transformer works, right? Okay, I think that's it for today. Thank you very much. I hope you learned something new. Okay, this is the next chapter. And good luck in your chapter 3 while your teacher is teaching you. All right, I hope the previous session that you have in chapter 3 is going to help you in learning and understanding more of what your teacher is going to teach you this week and next week and the following weeks in the class. Okay, thank you so much. See you next week. Bye-bye.